Hello everyone. In this video we will continue to examine topic 5.4, the magnetic effects of electric currents, and in particular we will continue to discuss charges moving in magnetic fields. So, notice that as a consequence, that like all things moving in circular motion, the work done on the particle by the magnetic force is actually zero. How do we find that? Remember that the work is equal to F dot S, or Fs cosine theta, and in this particular case, the angle between the displacement and the force for a charged particle moving in a magnetic field is equal to 90 degrees. And as a result, cosine theta is zero. Notice that this displacement in this particular derivation is written as v times delta t, but so the direction of the displacement is always the same direction as the velocity at any point along the circle. Notice that as a result, no work is done by the magnetic force, and the kinetic energy is constant. So it doesn't speed up, it doesn't slow down. That means no work is done on or by charges moving in a magnetic field, and this is super important long term. This means that when the charge is simply moving in uniform circular motion in a magnetic field, it actually doesn't take any work to keep them there. They will simply move in a circle until otherwise disturbed, which is sort of not a state we normally associate with things with an unbalanced force on them. So that's an important conclusion. Notice we can also answer the following question, which is what happens to a charged particle if it's moving at an angle to the magnetic field? So we're not going to analyze this mathematically. You won't be expected to analyze this mathematically, but you could actually. So what happens if V is at an angle to the magnetic field? Well, consider that velocity for a second. Part of that velocity, one component of that velocity, will be a constant velocity in the same direction as the magnetic field. So if V and B are, shall we say, or at an angle that is not 90 degrees, then part of that velocity will be in the same direction as the magnetic field, and part of that velocity will be in the perpendicular direction of the magnetic field. And so the part of the velocity that is parallel to the magnetic field will not change at all. It will simply remain constant, and this gives it a constant velocity in the same direction as the magnetic field. And then the part of the velocity perpendicular to the magnetic field will induce uniform circular motion in the plane perpendicular to the magnetic field. So in the sort of vertical plane, it will undergo uniform circular motion sort of up and sort of at a disk perpendicular to these magnetic field lines. The end result is what is known as a helical path. So it'll travel in a spiral steadily at a constant rate along the direction of the magnetic field lines, but in uniform circular motion in the plane perpendicular to those magnetic field lines. And so, big picture, charged particles move in spirals around the magnetic field lines, or in helixes around the magnetic field lines. This has a direct, real-life and wonderful, beautiful consequence, which is as charged particles coming from the solar wind, which is a stream of charged particles that is projected out from the sun, they hit sort of nearby the Earth, or the area around the Earth, and they spiral along the directions of the magnetic field lines of the Earth. These magnetic field lines take these charged particles at high velocities down into the atmosphere in the at the northern pole and at the southern pole. And when those charged particles run into the atmosphere, into the atmosphere, they release high energy radiation, which we know as the aurorae, either the aurorae borealis, which are the aurorae in the northern hemisphere, or the aurorae australopithecus, or something like that. I'm sorry, I didn't look up the term. But those are the aurorae at the South Pole. And so what you're seeing is the photons released as a result of the collisions of the charged particles coming in from the sun, spiraling down along the magnetic field lines. And they produce these beautiful aurorae.